Linear Algebros, it's Mr. C here, and I hope you're ready to boss up with some vector properties. Indeed, these are going to be some properties that apply to vectors in higher dimensions. And as you can see here in this table, we've got vector u, having components u1 through un, and vector v having components v1 through vn. And these two vectors are assumed to be from n space, so we're definitely taking it higher, to a higher ground.
It's over, Anakin! I have the high ground!
And k is going to be any scalar, so remember that's just a real number.
Affirmative.
So I'm going to share with you some of the most important properties, but later on I'll display on the screen some additional properties that come from our textbook. Let's start with property 1, u plus v. So we want to think of this as two vectors in component form being added together. So we can write it as vector u with the components u1 all the way down to un being added to vector v having components v1 all the way down to vn. And the way that you're to add these two vectors together is via corresponding components. So we would take the first component of each vector, in this case u1 and v1, add them together. So the component of the sum, the first component that is, would be u1 plus v1. And then we'd do the same thing with the second component, so we'd have u2 plus v2 all the way down until we've added up the corresponding nth components of each. So we'd have un plus vn. Next, we'll move on to property 2, which is a scalar multiple times the vector u from n space. Let's first write this as k times vector u in component form, so parentheses u1 all the way down to un. And the way that we can scalar multiply a vector in component form in any dimension is by distributing the scalar to all of the components of the vector. So the result would be parentheses k u1 all the way down to k un. Now something that I want you to notice is that this is pretty much the same way in which we do these operations with matrices. So for example, if you look at property 1, we add the two vectors that are in component form via corresponding components. And that's basically what we did for matrices. We add matrices that are the same size by adding corresponding entries. And likewise for property 2, when we scalar multiply a vector in component form, we multiply each component by that scalar, and that's exactly what we did for matrices. When we scalar multiply a matrix, we multiply all the entries by the scalar. So continuing on, we're going to do u minus v, and I'll jump straight to the formula for this. It'd be parentheses u1 minus v1, comma, dot, 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 all the way down to un minus vn. So you subtract corresponding components. The last property in this table is a scalar times the sum of two vectors. One thing that you can do is you can distribute the scalar to each one of these vectors to make this look like k times vector u plus k times vector v. And I'm going to replace both the vector u and v with their component forms. So this would take on the further form k parentheses u1 comma all the way down to un plus k times v1 comma dot 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 all the way down to vn.
Lord have mercy.
And then based on property 2, you can distribute the scalar to all of these components, both from u and the scalar k to all the components from vector v. And at the end of the day, we'd have the following sum, parentheses k u1 plus k v1, that's the first component, comma, dot, 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 k un plus k vn. Okay, so hopefully you're finding these some awesome vector properties.
Nope.
We're going to go ahead and put them to use with a couple of examples. The first one being let u and v, which appear to be vectors from 3 space. So u is 4, 3, 2, and v is 5, 4, 8. Find the components of 2u plus 3v. Now, as a little Easter egg, not Easter egg, but what's the word I'm thinking for? A spoiler alert. There we go. Okay, so as a spoiler alert, an expression such as this is known as a linear combination. And I'll explain why it's called that at a different time, but I just kind of want to get your feet wet with this. To do the problem itself, what we're going to do is we'll replace both vector notations with the component forms. So this would equal 2 times this 3 space vector having components 4, 3, and 2, plus 3 times that 3 space vector v having components 5, 4, and 8. Next, distribute the scalar, both the 2 and the scalar of 3, to get these vector components, 8, 6, and 4 for the first one, plus 15, 12, and 24. And based on the table above, to add these two vectors together, we combine corresponding components. So the first component of this resulting sum would be 23. The next component would be 18. And then the last component would be 28. And that right there is our final answer. Okay, so let's move on to the second example here. In this one, they give us 3 vectors. Vector u, it's a 3 space vector, components negative 3, 1, 8. Vector v, components 6, 0, negative 7. And vector w, components 2, negative 1, negative 4. And they want us to find the components of negative 7 times quantity vector v minus 3w.
We must stay focused, brothers.
So it looks like we're not going to involve the vector u in this one. My apologies to vector u.
Oh, sorry.
But let me just jot this expression down. We've got negative 7 quantity v minus 3w. And the trick to starting this out,
I'm going to do what's called a pro gamer move.
is to distribute the scalar of negative 7
Negative.
to both of these here. What this would look like algebraically is negative 7v, and then we do have a double negative that we can consider here. We could write that as plus 21w. And then we'll replace each vector with its corresponding components. So negative 7 times the component form of v, 6, 0, negative 7, plus 21 times the components 2, negative 1, negative 4. And again, based on a property from that table above, we can go ahead and distribute the scalar negative 7 to those 3 components and the scalar 21 to these 3 components to get parentheses negative 42, 0, positive 49, plus 21 times 2 is 42, comma, negative 21, comma, negative 84. All right. Last but not least, we'll add corresponding components to get the final answer of 0, comma, negative 21, comma, negative 35. And these would be the components of negative 7 times quantity v minus 3w. I just want to make mention that there is an alternative way to do this.
Come on now, dog. Come on, man.
Which you could do, and I'll just title this over here, way number 2. you could simply just replace the vectors with their components. So we'd have -7, and I'm going to open up a bracket. The component form of v is 6, 0, -7, minus 3 times the component form of w, 2, -1, -4. And then you can just sort of operate with simplification via the order of operations. Please excuse my dear Aunt Sally, or as I like to say, please end my day at Schoolcraft. So to give you a little nudge, what you might think about doing is distributing the 3 to get -7 bracket component form of v 6, 0, -7 minus the scalar multiplied component form 6, -3, -12. You would then combine these two vectors together, and then last but not least, you would distribute the -7 into each one of the components. Alright, so let's see what that looks like. This would equal -7, and then combining corresponding components here, we'd have 6 minus 6 giving us 0, comma 0 minus -3, so that's a double negative there for +3. And then we'll have -7 minus -12. So that's a double negative right there. -7 plus 12 is 5. And then we'll distribute the scalar to get these components 0, -21, -35. That's the exact same answer that we got when we cleaned the expression up with algebra to begin with. So you get to choose whichever one you prefer, but either way, I hope you're feeling pretty bossed up. That's the end of this video. Let me know if you have any questions. Otherwise, thanks for watching, and I'll see you next time. Take care, Linear Algebros.